Gary Parker here. This week, week 3 in Math 95, we're going to be finishing up chapter 2 and getting ready for the test on chapters 1 and 2. If you haven't already taken a look at the sample test at the end of the week, please do so. So after chapter or module 2, you'll see unit 1 exam, and there's a practice exam here that you can play around with. Please do that soon. So last week, introduction to functions, I'll review a little about right now, but mostly what I'm going to do is go over linear functions and graphs, how to compare them to data, and then using those models to make some predictions. So let's get busy. Textbook is a good thing you should be looking at here. There's lots of examples on what it means to be a function graphically. Must pass a vertical line test. Vertical line can hit at most once, because any x value can be traced to no more than one y value. 1x, 1y. But here, a particular x value has 1, 2, 3 points off this vertical line, so this graph here is not a function. Function notation. So if something is a function, as far as an equation goes, we can write things like y is a function of x. Mostly we're going to be playing with linear functions, so let's take, for example, y equals 2/3 x minus 2. Now, for any x value we plug in here, we're going to calculate a y value, and we're going to all agree that it's a single number. And so that means it is a function of x. So I could, instead of writing a y, I could write f of x, making it clear that this expression is a function. And function notation is good for substitutions. For example, suppose I want to calculate the y value when x is 3. All I have to do is write f of 3. So here that means x is 3, what is y? And so I can use the equation above to plug in. So 2/3 times 3 minus 2. 2/3 times 3 simplifies to 2. 2 minus 2 is 0. So we just calculated that f of 3 is equal to 0, which means the graph has the point, oops, wrong order, 3, 0. So notice when I write it this way, I make a point. X is 3, y is 0. So function notation can be pretty handy. Let's take a look. As far as linear functions go, a general linear function looks like this. Some number, we usually call m, times x, plus some other number b. And m is what we call the slope. Slope is also known as a rate of change. Many people know slope as rise divided by run. And rise is the vertical change, so that's the change in a pair of y values. And run is the horizontal change, or the change between a pair of x values. So that's why it's called a rate of change. Rate is a fraction, and there's a change in the top and bottom. So if I had a graph, and we had a point, say, over here, and another point over here, and there's a line that goes between them, the slope, here's my rise, and then here's my run. So if this is my first point over here, I might call that x1 for first point and y1 for first y value at that point. And this one over here could be, say, second point, so that'd be an x2 comma y2. Then the change in y would be take that second y value and subtract the first y value. Right? That'll give you this vertical distance there. Divide by the change in x to get the horizontal distance. We'll just take that second x value, subtract first x value. Things that are important here, y's have to be in the top, x's in the bottom, and the points line up vertically. So that's right there, 0.2, and that one right there is 0.1. So let's graph this one right here. So I'm going to do that by whipping out a piece of graph paper. Let's see, my magic board has some graph paper hiding here somewhere. See if I can get it. And let's do the medium print maybe. All right, that'll work. So when you graph, you should always throw an axis in there. So I'm going to put, just one color, the x-axis somewhere in the middle here, the y-axis, excuse me. And we'll throw the x-axis over here, say. And a ruler's not a bad idea. Whoa. All right, so here's my y-axis, here's my x-axis. To graph, you need some points. So we're going to graph that function I just had a moment ago. F of x equals 2/3 x minus 2. And one way to graph is by making a table for x and y. So I plugged in 3 earlier, so I'll put that down here. I have 3 and 0. And I might try x equals 0. So if I plug in 0 here, f of 0 is 2/3 times 0 minus 2. Well, that's 0 minus 2, which is minus 2. So I get the point 0 minus 2. And I could plug in any number like 1, and then I have to deal with fractions. Not a huge deal. So for fun, I'll plug in 1. F of 1 would be 2/3 times 1 minus 2, which is 2/3 minus 2, which is going to be 1 1/3. And one more. So since there's a 3 in the bottom, if x is a multiple of 3, it's going to be easier to work with. So I think I'll try -3. And I'm just going to do this in my head if you don't mind. 2/3 of -3 is -2. -2 minus 2 is -4. So I believe -3, -4 is on my graph. So I have to decide on a scale and graph this. So I think I'll go with every other one will be a unit. So then let's see, I have black right now. So this would be 1, 2, 3. That will be 4. 1, 2, 3, 4. You don't have to label everyone, but you got to label enough so that you can look back at it or someone else can look back at it and know what the heck's going on. All right. And my points. So let's see, what do we have? We have 0, -2. Right, that's my y-intercept here. And then I have 1 for x, 1 1/3 for y. So here's 1 for x. That's 1 1/2. 1 1/3. That's not right. It is -1 1/3. Oops. -1 1/3. -1 1/3. I knew that wasn't lining up. I was thinking about this next point here as I was plotting that. And 0, 3 is here. So one of these 3 was wrong. I was pretty confident about plugging in 0, and that earlier one we did felt pretty good in my head. But all right, so let's see if this works out. 1 goes with -1 1/3. That looks more like it. So somewhere about there. And what's the other one? -3. 1, 2, 3, down 4. So remember, every other unit. So 1, 2, 3, 4. So it should be right around here. And it looks like those points line up pretty good. And I was hoping they would because they have a slope there. So let's see if I can get my line tool. So here is my line. And let's make that line a different color. Oops, what happened? There we go. Let's make it blue. All right. So things worked out well. So just a note, if you know it's a line and you can see the slope and the y-intercept, another way to graph this would just be to note that 0, -2 is the y-intercept. So plot it, and then use the slope. So this says to rise 2 and run 3. So if I go up 1, 2, then I should run 1, 2, 3, and end up at that point. And then 2 points make a line. Now just a note here, the slope, m, is 2/3. I could also view that as -2 over -3, because a negative divided by a negative is still a positive. So that would say drop 2 and go left 3, which would put me at that point right there. So either way, I get the right slope. All right, so graphing utility next. So my recommendation is Desmos. And Desmos has a calculator, and since I've been there before, my computer jumped right to it, so let's get there otherwise. So if you just search for Desmos, you could click on graphing calculator or go right to their main website, and right away they say, hey, check out our graphing calculator. And it's pretty nice. So here I'm going to enter it as a function, f of x, f of x, there we go, equals 2 divided by 3. It makes a pretty fraction. Arrow over to the right, or you could click over there with the mouse, and then type your x, and then subtract 2. And there it is. And Desmos is kind of nice because it will give you special points on the graph. So I can say, hey, it'll give me the intercepts, which is pretty nice, automatically. And then if I want other points, I can use function notation. Like suppose I wanted to know what is f of 1. Desmos calls it -1.33333. So it gives me approximations as decimals, not fractional values. But is f of -3. And it says, hey, that would be -4 down here. If you want to make that into a point, then you have to type the point starting with parentheses. Type the x value, comma, type the y value, and it will plot that point for you. You can also use parentheses in a point, or a function notation in a point. So for example, let's suppose I want to graph the point 6, and I haven't calculated the y value yet, so I can just comma and say the y value is f of 6. And the reason I can do that is because up above in line 1, I said this is what f does as a function. And so Desmos will calculate that for me and find that point and tell me what the y value is once I click on the point. So function notation is pretty powerful. It's used in a lot of different circumstances, not just a graphing calculator. So let's look at another example. So many times, relationships between things are functions, meaning given a certain year, there's so many people in a town, there's so much garbage produced by those people, and so on. Functional relationships are all around us. So consider the amount of garbage, we'll call that capital G, in tons per week, is produced by a city with a population. The population's P. Catch. Population P is measured in thousands. So we can write this as a function, and the function can be written a couple of different ways. Here it says capital G equals f of P. We could also write it as f of P equals the garbage. So this function, given a population of a town, is supposed to spit out for us the garbage per week that they produce. Now the catch on P here is that it's in thousands of people. So if somebody tells me their town has 25,000 in it, in this example, P, the input, would be 25, because P is measured in thousands of people. So there's 25,000. And then for that town, the garbage is 6. And notice that's tons per week, which is exactly what I want. Capital G is tons per week. So again, P, that's my input. It's also known as the independent variable. And G, that's my output. And that's called the dependent variable. So this is like my X, and this is like my Y. So I could write this as a point. XP in this case goes first, and G, the Y value, goes second. And so that would be given that there's 25,000 people, they produce 6 tons of garbage per week. In function notation, I could write it as, if I plug in 25,000 people, the function should spit out 6 tons of garbage per week. Okay, so here's that as a point, given the information. Here's that in function notation. Just trying to get used to function notation here. Let's do another one. So I did a little research after that, just trying to take a look at garbage in the United States. So I went to the EPA, Environmental Protection Agency, for the US government, and they had some data on municipal waste. And they claimed in the year 2000, there were 243 million tons of garbage. That's a lot of garbage. In 2000, I think people in the US, there were probably like 250 million people. So that's roughly like a ton of garbage per person per year produced. Ton of garbage. That's a lot. See how many, my car probably weighs what, 2-3 tons. So my family probably produces, if we all produce the same, a car of garbage a year in weight. Ouch. So what I want to do is I want to graph this data and see what it looks like. So I'm going to do that. Now, plotting 1960 is kind of a pain in the butt. So usually what we do when we're plotting years is we go to the first year that we have and we say that's year 0. So I'm going to make a new column here. I'm going to call it X. And X is going to be years after 1960. So that'll make 1960 years 0, 1980 is 20 years later, and 2000 is 40 years later. And those are the points that I'm going to enter into my graphing utility. So back to Desmos. And let's just get rid of these guys here. Start over. So I want to add a table. I could plot them as individual points, but a table is just easier. So my X is 0, and the first was 88.1 million tons of garbage. And then 20 years later, in 1980, it was 151.6 million tons of garbage. And then another 20 years later, so 40 years later, it was 243.5 million tons. So years after, X is my years after, and then 1960, and Y, million tons of garbage produced in the US per year. So I can't see those right now, so I'm going to have to adjust my viewing screen here. So I could zoom out until I see the points, but the scales are pretty different here, so that might not be the best way, but I could keep doing that anyway. Oh, and there's my 3 points. Another thing I could do is I could go to the wrench to configure the screen, and I could just say, hey, for X, let's go from, say, like -10 to 100 years after 1960 to project into the future. And for Y, maybe there, let's say I need to get up to 240, so maybe we'll go up to 300 for the max. And the minimum, I could have, like, I don't know, -100, say. All right, let me close that. All right, so there's my points right there. And they kind of sort of line up from there to there. So I could find that line, and that's not too hard, so we'll do that next. So I'm just going to pick 2 points. I'm going to pick the first and the last point to find the line through. So back to my worksheet. So again, here we're going to focus on the first point and the last point. So let's highlight those. There we go. So I want this point here, and I want this point down there. So to get the slope, we need our change in garbage. So that's going to be 243.5. minus 88.1, there we go, divided by a change of 40 years. So that's not too bad. Just got to do that calculation for the numerator, and Desmos can handle that. It's a calculator. So I asked Desmos, what is 243.5 minus 88.1? And Desmos says it's 155.4. There we go. So my slope is 155.4 over 40. So cleaning that up again, back to my calculator. I want to take that number, 155.4, and divide by 4. Now I could have calculated this all in one shot. I would just have to use parentheses to do that. So on your calculator, you can use the parentheses button, or if you have a keyboard, type parentheses 243.5 minus 88.1. So I have to put parentheses around the numerator because it's complicated. Once I hit divide, Desmos puts the fraction bar, which means I kind of don't need the parentheses, but can't hurt. And I should, oops, I divided by 4 above, 40, and the numbers match. So about 3.885, 3.9, however you want to round it. So back to my notebook. So this is approximately, I'm just going to call it 3.9. And so that's my slope. Now my y-intercept, since I have a year 0, is the 88.1. So I could say in this case, if I use g for garbage instead of y, g equals 3.9 times x, the years after 1960, plus start at 80, come on pen, 88.1. So I'm going to enter that in and see if it looks okay with my data. Let's clear these numbers out. We don't need those anymore. Okay, so we're going to enter f of, or actually we can call it g of, that'll work too, x equals 3.9 rounded times x, or just x. Some computer systems, if you type an x by itself, freak out. Others want you to type times x. This one goes either way. Plus 88.1. And I should see that pretty much goes to the first point for sure, and it approximately goes to the second point. It looks good on this screen because the point and line are so fat. But remember, we did round that. So if I ask the computer here, what is capital G of 40? In other words, how much garbage is there 40 years after 1960? It says 244.1 instead of 243.5 because I rounded there. Okay. So finding slope of a line. Now, if, let's suppose, we didn't have the y-intercept and we had to use some other point for it, how do we find the y-intercept otherwise? So the trick on that, finding a y-intercept, if you just have, let's say, the slope and a point. The key there is, let's say, just like the previous example, our slope is 3.9. And instead, let's take, I have the point 40, comma, 243.1. So because the 3.9 is rounded from the data, I won't get the exact answer, but I'll get close. The trick is to use this famous equation right here, y equals mx plus b, and to make a note that you know a y value, right? And you know an x value. And you know the slope. So if you plug in those three numbers, b is the only number it's missing, and you can solve for it, no problem. So in this case, I would say, all right, y is my 243.1. That's supposed to be equal to the slope times the x value, and then plus the y-intercept. So to get the y-intercept alone, all I have to do is subtract this sucker to the other side and make the calculation. So I'm going to make that calculation right now in my Desmos calculator. So I'm taking that 243.5 and I'm taking away from it 3.9 times 40 years, and it gives me 87.5. Now again, I mentioned that we weren't going to get exactly this y-intercept. We're close though, because that 3.9 is the rounded slope. I think the actual number was, what, 885. So if I use the actual number without rounding it, I'll get a better exact answer. If I round any number and do a calculation, I get an approximate. So 87.5 is close to 88.1, okay, in this ballpark here. Okay, so playing with lines. So most of this, aside from the function notation, all the stuff I did with lines here should be reviewed. So hopefully you remember that from a previous math course, and this just lit up those parts of your mind to remember those. Next thing I want to look at is the idea of linear regression. So that's having a computer find a model. So linear regression. Linear regression is also called a line of best fit. These 3 points that I started with here don't exactly line up. So I'm going to turn that off and that off and that off. Oops, I deleted them instead. That's okay. They don't perfectly line up. In general, when you get real-world data, they don't perfectly line up or form a perfect curve. But often there's a line or a curve that's pretty darn close to them. And so what linear regression does is it tries to find a line through here that minimizes how far off the line is from each point. Okay, so you could find a line through the first point and the last, or the first and the second, or the last and the second, or you could find some line that kind of splits the difference in between them. And that's what linear regression does. It's a mathematical technique for kind of splitting the difference. If you want to learn more about how the slope and the y-intercept is calculated for linear regression, then you got to take a few more math courses to get up to that. That's usually covered in a second course of statistics, which is often after college algebra, Math 111. But here the program will do it for me. So in Desmos, to make that happen, first I need a table of numbers plotted. Once I have that, I say, okay, my y values are called y1. To have the computer make a model for you instead of you typing it, if you type it, you have to type in equals next. If you want the computer to do it, you hit the tilde symbol, that little curly thing there. Once I do that, I tell the computer I want a slope called m, and m needs to be multiplied by the x value of the points, that's x1, and then I also want a y-intercept, and we call that b. And so then it tries to find the best line that splits the difference between the points, minimizing how far off the line is from each point. So the first and last point are a little high, the middle points are a little low, so it's splitting the difference in between there. It's minimizing that vertical distance between the point and the line. And then the model can be used to make predictions. So for example, if to use this, I would create a new function called f of x, and I would use their m and their b, which I can just call m and b. And so it made this black line that sits on top of the purple one, because it's the same m, that 3.885, and the same b. So notice that's pretty darn close to the slope we found, coincidentally, because it's a simple example with 3 points. Then I can say, all right, what is f of 40, or 20, that middle one? It says it's 161.06-ish, and the actual value is 151. Right? If I plot that point, parentheses 20 comma f of 20, so that says here's my x, plot the y with the same thing. See that point right above? So I'm just about 10 off on that. That's called the error and approximation of my model. But I can use the model to predict into the future. So for example, what does this model say the amount of garbage in 2010 was? So 2010 would be 50 years later. So I could plot the point 50 comma f of 50. And then that's this guy right here. So my model says in 50 years after 1960 or 2010, there was about 278 million tons of garbage. So I can use it to predict. It turns out I looked this up. The actual amount of garbage, according to the EPA in 2010, so 50 years later after 1960, was about 250 million tons of garbage. Okay, so my model is a little off. So maybe we're getting better at recycling, and so we don't have as much garbage as our model predicted based on the data from 1960 to 2000. So this is the actual data point. This is what my model predicts. But notice I didn't use this orange point in my data analysis here. Okay, and if I did, I probably would have got a better line to predict the future. So there we are. So we made a linear model. We tried to make a prediction out of it. Now we could take it a little bit farther. So I'm going to call this 3.9 and 83.4. So let's go back to my notes. So according to my computer here, the line of best fit for the amount of garbage is about 3.9 times x years after 1960 plus, what was it, 88.4, go back and look, 83.4 about. And so we can use this to make all kinds of predictions. On the test, I won't make you calculate the model. I'll describe the situation. I'll just give you the model, and you can do things with it. Like we wanted to predict how much garbage is there in 2010. So in 2010, my x would be 50. So I just needed to calculate how much garbage is there 50 years later, which is just plugging into this equation, which I asked the computer, Desmos, to do for me. So 3.9 times 50 plus 83.4. And that spit out something like 270 something. What was that? 277 about. Another question I could have asked here is, when will the amount of garbage produced be above 300 million tons? So there I'm saying G equals 300. What is X? So in that case, I would have to solve an equation. And the computer can kind of sort of do that, but it's almost always, it's sometimes easier to do it by hand. So here I want to know for what X value. I don't know what year it is yet. What was that? Y-intercept again, 83.4. When will we reach 300 million tons? And I can just solve this equation by first subtracting the 83.4. And then dividing out the 3.9. So let's see, where are we? 3.9 is going to be equal to, what's that going to be? 216.6, I think. Oh, and then divide by the 3.9. And we can come up with a number. So let's check and see what that is. Remember, Google is a calculator. 216.6 divided by 3.9. And I get about 55.5 if I round. So about 55.5 years later. And that seems reasonable to me, because my model says that 50 years later, there's going to be 277 million tons, which is a little less than 300 million. So the numbers seem reasonable. I could then look at my graph to see if that point seems in line with the other points. So back to my graphing calculator. if I plot the points, 5.5, comma 300, I should see it sits pretty much on the line up here. There it is right there. So a graphing utility can be really helpful to explore data, to explore equations, to help double check things that you did in calculations. So play around with Desmos, have some fun with it. And we just covered sections 2.3, 2.4, 2.5, and 2.6 are combined. So have fun with that. There's a little bonus assignment there if you want. Check it out. And then please check out the practice test as soon as possible, like today. Even if you're not done with chapter 2, start taking a look at it now. Take the test this week if possible. Otherwise, take it on Monday, which is what, the 29th of January. Have fun, do good math. I'll catch you soon.